In this lecture, we are going to start looking at a particular type of circuit that is going to try to maximize the gain available from an amplifier. So far, you would have seen that the common source amplifier gives you the maximum available gain that you can get. So you will need a bias voltage VB at the gate of the transistor, and the small signal is also applied here. The output is of course taken at the drain, so maybe I'll call this the DC voltage is capital VO plus the AC voltage is small VO. So we know that the gain of this circuit VO by Vs is minus GMR. Now suppose I want to get more and more gain from the circuit, I will need to either increase the GM of the circuit or increase the resistance of the circuit. Now there is a limit to which you can increase the GM, primarily because you don't want to keep increasing the power by increasing the current. So if I want to increase GM, I need to increase current, which means power consumption would increase. I do not want to do that. The other thing that I would need to do is increase the width to length ratio. Otherwise I would need to increase the if I wanted to increase GM, if I wanted to increase the gain of this circuit, so this is A, I increase A in two ways. I need to increase GM or increase R. Now I can increase GM by increasing the current or increasing the W over L of the transistor. Now all of these both of these have certain issues. If I increase I, of course I'm increasing the power consumption of the circuit, which I do not want to do. If I increase the width over length of the device, I'm actually making the device slower because I'm increasing the capacitance of the device, so the bandwidth gets affected. So this affects power and this affects bandwidth. I do not want to affect either of these as much as possible. If I increase R, what happens is, suppose I keep the current consumption constant and width and length of the transistor constant. If I increase R, what I find is that VO, the DC value, is VDD minus I naught R. So if I keep increasing the value of resistance, this keeps reducing. So the DC voltage at the gate of at the drain of transistor keeps reducing. Eventually, whereas the VB stays constant because the current is constant. So far you would have seen this type of common source amplifier, and you can write down the various DC voltages in terms of the DC currents and so on. But the voltage that we are interested in is the output DC voltage, which is VDD minus I naught R. And we know that for this circuit, the small signal gain VO by Vs is minus GM R. Now let us say that we are trying to increase this gain, the magnitude of this gain. So this is what we are going to try to do. Now there are of course only two parameters that you can touch. So you can increase the transconductance. So this can be done in two ways. I can increase ID, which I do not want to do, because this will increase power. This increases the DC power consumption, which I do not want to do. The other way I can increase GM is to increase the width over length ratio, and this will increase capacitance, and of course more importantly decreases the bandwidth, which is also a problem. I want to keep the bandwidth constant. And the other way to increase the magnitude of VO by Vs is to increase the value of resistance. Now, on the face of it, this seems fine, but please note that the output DC voltage reduces linearly with increase in resistance. In other words, the actual implication of this is that M1 moves closer to the triode region, to the triode boundary, and therefore what I'm actually giving up is swing limit. And this is also a problem. Now let us show this graphically so that we get a better understanding. I am going to show this on the plot of ID versus VDS. So we know that for a particular VB, the ID versus VDS plot looks like this, and initially I might have been biased somewhere here, VDD minus I naught RD, but now if I increase R for the same VB, I will move closer and closer to the triode. Let's say this was the triode boundary. I will move closer and closer to the triode boundary, which I do not want to do. Now, it turns out that you need a large value of resistance without changing the bias voltage at the output. You may remember from your basic circuits course that if you take an NMOS transistor and bias it using a current source, the gain of the circuit, so VO by Vs, is nothing but minus GM RDS, and this is the intrinsic gain of NMOS. So you may remember that this is the largest gain that you can get from a transistor. So what we want to achieve is we want to get a common source amplifier which has a gain that is as close to this as possible. This of course does not have strong limitations on output bias point because the current source can have a large range of voltages across it without changing the current. Now our job next is going to be design this current source. Now what we want is we actually want a current source of some value I naught, right? So this was I naught. Now please note that the current source is taking some current from VDD and pushing it to ground, and obviously it has a constant voltage independent of VO, which means that R out is large. So these are the characteristics you want from a current source. So many of you might realize that a PMOS transistor with its source connected to VDD and its drain connected to some VB1, I'll call it VB1 or VB2, with its gate connected to VB2 will have a current I naught that is related to VB2 in the following manner. In this way, right? So I need to choose VB2 and W over L of the PMOS transistor such that it has a current I0. What is the output resistance seen at the drain? This is of course the RDS of the PMOS, which can be designed to be very large. So now we are going to replace the current source with a PMOS transistor that is biased for a particular current. So this is the amplifier that we have been looking for. So let us say the NMOS transistor is M1 and the PMOS transistor is M2, and I'm going to say that the NMOS transistor has a bias voltage VB1 and a signal voltage Vs applied to the gate. The PMOS transistor has some voltage VB2 at its gate. Now you need to apply a voltage VB1 such that the NMOS transistor has a current I0, and you need to apply a VB2 such that the PMOS transistor also carries a current I0. If you were to draw the small signal equivalent circuit, so before we draw the small signal equivalent circuit, I want to emphasize again that VB1 and VB2 have to be chosen very carefully so that the two transistors have the same current I0, and there is one additional condition that is very important. I'll write it down. Both M1 and M2 are in saturation. This is a very important condition, as you will see. So you need to choose VB1 and VB2 very carefully. Now let us draw the small signal equivalent circuit. So I have a voltage Vs which is applied to the gate of M1, and there is a current source which is GM1 VGS1 and RDS1 of M1. So this is the drain of M1. This is of course the source of M1. Now please note that the drain of M1 is connected to the drain of M2, which also happens to be the output voltage VO. Now what happens to the current source of M2, the current, voltage control current source? Clearly the small signal voltage at both the source and the gate of the PMOS transistor is 0, and therefore there will be no signal current generated by the GM portion of the PMOS transistor. Now you can write the expression for VO by Vs. This is nothing but minus GM into RDS1 parallel RDS2. So now this can be very, very large. And in fact, this is only around half of the intrinsic gain of the transistor. This can be much larger than GM times R, because the value of RDS is normally much larger than the value of R. What about the bias point? Please note that the output voltage VODC, okay, is not limited by RDS. Of the PMOS transistor. So this is an important distinction compared to the case with the resistor, where the output DC voltage was related to the value of the resistance. In the case of the PMOS transistor, the output bias voltage can vary over a large range of values without affecting the value of the current or the performance of the PMOS transistor. Now we can go one step further to complete this whole scenario. We can go one step further. Of course, you can also imagine a scenario where you use the PMOS transistor for getting some signal gain also. So what do I mean by that? In the earlier case, I was applying Vs here and I was connecting the gate of the PMOS transistor to small signal ground. But a question can be asked, why not connect the gate of the PMOS transistor to Vs so that you get small signal gain from the PMOS transistor also? And yes, definitely this can be done. So let us look at that circuit. So I'm going to, this is the circuit that will have Vs being applied to the gate of both NMOS and PMOS, and I will leave this as a homework, but you can draw the small signal equivalent circuit and show that VO by Vs will be minus GM1 plus GM2 times RDS1 parallel RDS2. So the gain of this circuit will be even higher than the gain of the previous circuit. Before we proceed further with this circuit, I just want to point out that this particular style of using a PMOS transistor to get more gain, you call this particular PMOS transistor by a specific name. This PMOS transistor is called an active load. So instead of using a passive resistor, a small signal passive resistor which is passive, the PMOS transistor actually has small signal gain. So from a small signal point of view, it is active, and this is such a way of using the circuit is called an active load. Now in this for this particular circuit, each transistor acts as an active load for the other transistor. Now an important condition is that both M1 and M2 should be in saturation. So only if both of them are in saturation will you actually get large gain. If any one of them goes into the triode region, you will not get large gain either for this circuit or for the previous circuit. Those of you who would have taken a course on digital integrated circuits will know that this circuit is actually used in digital design, not in a small signal fashion, as the CMOS inverter. In those cases, you do not apply a small signal voltage at the input, and you don't take a small signal voltage at the output. And I encourage all of you to go back and draw the V out versus V in DC characteristics for this circuit. So if you were to take this circuit and apply a DC voltage V in and look at the output DC voltage V out, if you plot V in versus V out, I will give you the curve here. I encourage you all to study the circuit and analyze how this happens. So V in is normally varied between 0 and VDD. So if you quickly look at the circuit, when V in is very small, below the threshold voltage of the NMOS transistor, the NMOS transistor is completely cut off and it cannot conduct any current, and therefore the PMOS transistor also has to be non-conductive. However, the source gate voltage for the PMOS transistor is very large. So therefore the only way this can happen is if the drain source voltage or the source drain voltage of the PMOS transistor is almost 0. So what you will find is that the output voltage till the NMOS transistor turns on, the output voltage will remain at VDD. There is no current through the circuit, so the output voltage cannot change, and the drain source voltage for the PMOS transistor is clearly 0. It is VDD minus V0. After the input voltage crosses VTN, you will find that the NMOS can conduct. Because the V out is very large, the NMOS will be in saturation region, but the PMOS will be in triode region. Now, before I draw the center portion, let us look at the other side. If you look at voltages between VDD minus VTP and VDD, you will find that the circuit is not conductive because the PMOS transistor is off, and so you will find that the output voltage is 0 and stays 0 because the NMOS transistor has a drain source voltage of 0. Eventually the NMOS transistor hits triode, and it starts to conduct with the PMOS transistor being in saturation. Now there is the center portion where both transistors are in saturation. Now this portion is the analog portion. In this region, both M1 and M2 are in saturation. And this is where you get maximum gain, because please note that the gain A, which is VO by Vs, is nothing but the slope of this curve. It is basically dVo by dVin. Of course, I have shown this in an exaggerated manner such that the gain is not very high. Okay. If you actually look at a typical CMOS inverter, if you look at a digital IC's textbook, you may actually see a curve that looks more like this. I have exaggerated the curve to show that you get large gain. You can actually get, in an ideal case, a CMOS inverter should look like this. This is the kind of curve you will see if you ignore channel length modulation. So this slope is minus infinity. If you ignore lambda, slope is minus infinity. In other words, the gain is infinite, clearly, because RDS is infinite. I have shown a case where lambda is very small. Lambda is very large for the curve shown. For an ideal transistor, lambda is 0 when you will have RDS equal to infinity. So there is a range of output and input voltages over which the both transistors are in saturation. This is called the CMOS inverter, and this can also be used to bias this can also be used to get very large gains.